Hello, everyone. For all the yoga aficionados, Ashtang is the very core of the yoga philosophy on the path to nirvana, samriddhi, kaivalya dham, or whatever we identify that ultimate bliss as. Here today, we intertwine Ashtang and yoga. How do you do it? We have an expert who's going to show us how that's done. Dr. Shailesh Kumar is the Chief Data Scientist at the Center of Excellence in AI ML Reliance Geo and is the perfect balance between academia and the business world. His expertise lies in the area of AI, ML, deep learning, and a host of other deep technologies. This expertise very well displayed in the AI solutions he's built across domains and industries. Please welcome today with us Dr. Shailesh Kumar.
Thank you, Drupti. It's my pleasure to be here.
Thank you,
Uh,
sir.
okay. Should we get started?
Yes, please. So, would
So,
you like to introduce yourself before we jump into the presentation a
yeah,
little more?
sure. Yeah, I'll do it. Let me just share my screen and then.
Sure.
All right. So, good evening, everyone. My name is Shailesh. I work with Reliance Industries right now. In the past, I have worked with Yahoo, Google, Microsoft, Fair Isaac, and Ola Cabs. Currently, I also work as a visiting faculty of machine learning at ISP and a program mentor for AIDS program in Geo Institute. So what I'm going to do today is talk about, summarize my journey of the last 20 years of AI into an 8-layer AI architecture. 8, therefore, Ashtang. And, you must have heard of the network stack, for example, that has a multiple layers of networking stack, right? There's a physical layer at the bottom and a application layer at the top. And that is the basis of all the Zoom calls and WhatsApp messages, because there is a layered architecture of networking. Similarly, I was, thinking about we are heading into a very complex world going forward, and we need a, sort of like a framework for understanding AI in a very holistic way. So that is the origin of this platform, this framework. And the second part of my talk, I'll talk about complex dynamic ecosystem, which is also the next 20 years of AI, what we are going to do, and how do we use Ashtang AI in a complex dynamic to build complex dynamic ecosystems, right? So we are all here because of amazing technologies that have come together, right? So the AI technology, the devices, the cloud, the connectivity, the IoT, and all of that. Therefore, we are in a very beautiful time, and the growth is exponential. And what we can do in the next 20 years, we cannot even imagine today. Like we could not have imagined that we could do a Zoom call 10 years ago, right? So it's an amazing time to be around, and people who will innovate great products will basically be using multiple of these technologies to put together a amazing product. So it's a very beautiful time on convergence of technologies. And among all these technologies, AI is considered one of the most path-breaking, right? And with the recent buzz around ChatGPT, everybody is now talking about AI. But ChatGPT is just a very small part of what overall AI can do. And this statement by Sundar Pichai is a forward-looking statement more than what we have already achieved. So what he's saying is going to be achieved in the next 20 years when every farmer, every student, every teacher, every patient is able to feel the impact of AI on their lives. Right? Today we have only done a few great things like build a search engine, build a chat GPT, recommend movies on Netflix or Amazon products, but we've not done anything which is socially transformative yet. And that is what the next 20 years of AI is going to be about from a use case perspective. So let me talk about that perspective, which is, that there are many ways to talk about AI, right? So one is algorithmic way of talking about AI. Another is what kind of data can you apply it on, so speech or text or whatever. Another perspective is what is the process of building an AI system end to end. Another perspective is what domains can you apply it in. So these are different perspectives in which we can think about AI. I'm not going to talk about any of these. I'm going to talk about the architecture perspective, right? What are the different layers in an AI stack, and why do we need them to think about complex ecosystems? So that is the journey. So this is the context, right? So now think about how the products are evolving. If you look at the products are evolving, product 1.0 are what we call programmed intelligence products, like a car or a washing machine. They're running on a very simple, flowchart essentially. So these are what we call product 1.0, which are physical, reliable, and programmed. They never improve over time. They just come as if they are programmed. The next generation product in the last 20 years, we have learned how to build products that can learn over time and become better with a lot of data coming in. So that's our product 2.0. They're mostly digital, and crowd intelligence is what drives these products better. And now, where we are heading in the next 20 years is what I call hybrid products or ecosystem products, like a smart city or or a smart ecosystem. And this is where this leap that we are about to take is going to drive us into the next 2 decades of what AI can do, what IT can do together to build such amazing products, right? And I'm talking about products like a smart city is a product, or connectivity as a whole. Telecom is one product, not like devices and cell towers, but the whole thing is one product. Entire refinery or a manufacturing unit is one product. The entire agriculture ecosystem of a country is one product, not just a drone. Or the entire healthcare ecosystem of a country with supply chain of medicines and beds and oxygen and all of that. Or how do you think of e-commerce is already an example of a complex ecosystem product. Yeah. So the point is, let me define what a complex ecosystem is, right? So if you think about these versus Google search, right? Google search is a very simple product, complex in a different way, but simple in a different way compared to these products, right? To a smart city, for example. So the idea is here you're dealing with billions of entities of very different types. So in a telecom, you're dealing with lots of, you have SIM card, devices, customer location, cell tower, fiber, all of that, right? So you have billions of entities of hundreds of types. And you're not just dealing with web pages, queries, and ads, three types of entities. You're dealing with billions of, hundreds of types of entities. Then you're dealing with trillions of interactions among them, right? People are joining the network, leaving the network, making a phone call, downloading data. All these interactions are happening all the time in a very asynchronous manner, right? So this is a very complex system. Then hundreds of metrics are at play. You have complex web of metrics, and we'll talk about that. Consumer metrics, operational metrics, business metrics, people on the ground metrics, sustainability metrics. So you have all kinds of metrics, and they're not independent of each other. And the next is you're driving millions of decisions every day of all types. It's not like Google search that given a query, what are the 10 blue links, what are the 10 images, what are the 10 ads, and all that. So they have very few decisions to make given a query. But in a complex system, the decision variety is also very large, right? And then you have lots of workflows that are running all the time, right? Like, you are executing something, you are handling an exception, you are increasing the efficiency, you are expanding the business. So you're running many, many workflows. And this is what a definition of complex ecosystem is, right? And we saw examples of that. Now we are at a place where we know that we are heading into such systems, but we have absolutely no idea how to think about an operating system for such a complex ecosystem. Right? We know what an operating system for a mobile phone is, for a cloud infrastructure is. But what is an operating system for a smart city or a telecom or a retail? We have a collection of APIs running somehow, but we still don't have an operating system. Yeah. So how do we think about that? And how will our AI thinking evolve to deal with this complexity? So that was the context. So now we are ready to kind of think about the 8 layers in the AI with those products of the future in mind, right? And think about, is what I do today just building a deep learning model for something, or deploying a chat GPT in some app? Is that what the end of AI is, or there's a lot more? And this is the talk where we'll talk about different kinds of AI coming together to build such products. So we start with layer zero, which is kind of like not one of the layers, but because we are all computer scientists, we think about zero as the first layer. And this is what I call the digitization layer. Even today, a lot of data is physical in nature. a handwritten note by a doctor, a printed report, blood test report, or a printed ECG report, or a printed X-ray. All this is physical data. So a lot of data is still physical, and we need a digitization layer to convert physical data into digital format, right? So this is not part of the AI stack, but it's a starting point so that at least all data is digitized. Now we'll talk about the 8 layers. So the first layer is what I call the interpretation layer, which interprets the raw data of any type into higher level semantics, right? Speech to text, image to object, and all of that, right? So interpretation is the first layer, and a lot of deep learning goes into these kind of models. The next layer I'll talk about is causality. Causality is what we do. Science is all about causality. Data science is also about causality. And we'll talk about different notions of causality. Um, the next is the prediction. Once you know what can cause what, now you can quantify how much of this causes how much of that, right? And that is a prediction layer. Prediction is different than interpretation, and we'll talk about that. The next layer is explanation layer, right? So without any explanation, in the future, models will not just produce an output, but they will also have to produce an explanation for that output. Why did you say so? Why is somebody's CIBIL score low? So you have to explain that because of this and this and this, right? And every outcome of a model has to be explained. So we'll talk about explanation as a layer 4. Now I will pivot into AI and control system thinking. So the next layer is what I call controllability. And the purpose of AI is not just to interpret, not just to predict, not just to explain, but to control, right? So when you think about autonomous vehicle, we are controlling it. When you think about running a plant, we are controlling it. When you think about tilting a cell tower antenna, we are controlling it, right? When you're running a refinery, we are controlling a lot of things. So controllability thinking is a subset of causality thinking, and we'll talk about that. Once you know what you can control, then you go into the simulation layer. And in my prediction, simulation will become a very important tool for complex systems, because you cannot just simply build an input output model. You'll have to simulate the whole thing, right? And that is the next skill set that we'll have to develop to simulate complex systems. The next thing is, once you know how to simulate, you can then do optimization and say, how do I optimize refineries? How do I optimize cell towers? How do I optimize, e-commerce and all of that? And once we know how to optimize, the last layer is what I call adaptation, which is really re-optimization when the situations have changed, right? So these are the 8 layers we'll talk about, and let's see how it goes. Yeah. And you will see the connection between them, why we need all 8 layers to build a complete system. Now, the first layer we said is digitization layer. It's not part of our system, but today we have a lot of ways to think about digitization, right? You can take a photo and that can be understood. QR code, scanners, OCR, and Google Books project, for example, converted a lot of physical books into digital books so that people can search and all that. Google.books.google.com, for example. So these were all large scale digitization exercises. Even today, a lot of companies have physical receipts, physical catalogs. How do we digitize them? Digitize doesn't mean PDF. Digitize doesn't mean JPEG. Digitize means extract information and put it in a database so it is searchable, right? So how do we think about it? All right. So now let's get the digitization out of the way. So assume all data is digitized. What are we going to do with it? So the first layer, the interpretation layer, is really about converting a large volume of shallow semantic data, like a whole video, into small amount of deep semantic attributes, right? So now if you're watching a movie, you can say this scene was about that, this scene was about that, this scene was about that, right? Although the raw data is very high volume of pixels in a 3D space, but the interpretation is very simple, right? At a much higher semantic level. Now, what is the inspiration for the interpretation layer? If you look at our own human intelligence system, the first line of defense, the way our brain consumes the data from the world, is through the five senses plus language. And now the only way it does it is because it has built amazing interpretation systems, right? The olfactory system, the visual system, the tongue system, they're all interpretation systems that interpret the raw data in the form of light, taste, smell into an pulse that goes into the brain. So the brain doesn't know how to smell or see, but the raw data gets converted in a format that the brain can consume. This layer is very important, and today we are building this layer across domains, across data types. So let me give you examples of that, right? So if you look at Spotify, what they have done, they have interpreted a song in terms of these 9 dimensions. So now they can convert a song into this kind of a representation. And now imagine, they have done this for all songs. Now you like a certain set of songs, they take the average of that. That gives them an idea of where you sit as a consumer of songs in that space. And when a new song comes, nobody has heard it or liked it at all. Still, they can tell that you're going to like it because that song sits in the same space near where you sit in that space, right? So you like certain kind of songs, therefore you're going to like it. So that's the power of what interpreting a song can do, for example, right? Then we do interpretation like speech to text interpretation, right? And text to intent interpretation. These are also interpretations. So we can interpret all kinds of data, right? Language and speech. We can interpret text in a different way and say this is semantic analysis of text and all that. We can also interpret text in the form of embeddings and convert text into embeddings. This is also a form of interpretation. So converting one form of raw data into another form of structured, smaller data, which is highly semantic, is interpretation, right? So in the right side, you can say that the first, although it's a wrong spelling grammar, the embedding of this is nearby the embedding of these. So these are all similar and these are all similar, right? So we can interpret text, we can interpret languages. We do this natural that, doing word sense disambiguation is very natural. Converting a piece of knowledge graph, language into a knowledge graph is also something we do all the time. When we read a novel or a paper, we forget the language and text, but we remember the knowledge that we extracted. So these are also examples of interpretation of text, right? Then we do interpretation of images, whether it's an image of people, face image, satellite images, medical images. We now have a very broad set of algorithms to interpret all kinds of images. Tomorrow we'll be able to tell what the breed of the dog, breed of the horse, emotion of the person, the brand of the shirt he's wearing. All that can come, right? So interpretation is very deep, and we can keep interpreting the same data deeply. Another form of interpretation we are doing now, these content companies are, TikToks and TikToks and all the others, right? Netflix's, YouTube's. They are now going and doing deep interpretation of their content and saying, I don't care about the genre of the movie. Tell me the genre of every scene, right? And tell me the people in the scene. Tell me the location of the scene. Tell me the sentiment of the scene, right? Similarly, if I look at the fashion world, they are interpreting dresses, for example, and saying what are the categories of dress, what is the pattern, what is the major color, neckline, and all that, right? So, what is the key art in building an interpretation layer is to understand what kind of raw content we are ingesting and in how many possible ways we can interpret. What are the dimensions of interpretation? So in media, people, genre, location, action, sentiment are the some of the dimensions. In fashion, category, pattern, color, neckline, shape, fit, whatever is the dimension. So it comes from domain knowledge. How many ways can you interpret something? Yeah. Let me skip that. So now let's talk about, let me skip this. So now the next thing is we'll talk about causality layer, right? So we understand that the first layer of AI is all about converting raw data into high-level semantics. Now we have seen speech, text, images, videos. How about gene sequences? How about time series data? How about satellite data, weather data, and space data? Everything we are able to interpret. So building a classifier or a regression model on complex data into a class is really an interpretation model. Yeah? And people think that's the end of AI and machine learning. We have done deep learning in speech, text, and vision. We are done. So now I'll take you through the next 7 layers of AI. Right? So the next layer is what we call causality. And if you think about causality, all of us work with causality all the time, right? When you go to a doctor and he's trying to figure out what caused these symptoms, He's trying to figure out what disease caused these symptoms. When I go to telecom and say caused this call drop, is it because the device is not well? Is it the coverage is low? Is the network load very high? So one of the skill sets of a future data scientist is to be able to talk to domain experts and say, you want to predict disease, you want to predict call drop. First, you tell me what are the possible causes. And now I'll build a model and the features to figure that out, collect the data. But this is the starting point. How do we think about drawing causal structures before we even touch the data, right? And saying this is what domain knowledge is telling me. Now, this is called multi-factor. That means one or more of these causes can lead to the effect, and we need to develop that cause and effect thinking. Yeah. Second type of causality is what we call cumulative causality. You may call it, regression models, right? So here, if I'm trying to think about demand of lab in a certain city, in a certain day, in a certain time window, what is the total demand? The total demand, cumulative, is a function of what campaigns am I running? Is it a commute time? Is there a stadium event going on? What is the weather? Is it a holiday? Is the competitor running a campaign? So demand is not just a simple thing to predict. You have to know many, many factors that will cumulatively affect the demand. You are going to see a total effect, not the partial effect. And you should be able to parse out that this demand is, 50% because of this, 30% because of this, 10% because of that, right? Same thing with supply. How many cars will be there in a location on a time? You should be able to say, okay, what are the current number of cars, incoming, outgoing, log in, log out, drift, cancellation. Therefore, it will all affect supply. How do we draw these diagrams using domain knowledge to say the sum of all this is the cumulative causality? The next kind of causality is what we call temporal causality. There are many variations of that. Some of them is about event to event, right? So an event has happened, somebody bought a printer, and after X number of days, they are going to buy a cartridge. And now you should be ready to say, oh, this is a type of causality I have built, grocery causality, every now and then, what's the frequency people buy a new car or a new cell phone or whatever. How do we think about event to event causality, right? Similarly, event to event in, for example, seeding the crop, harvesting the crop, what is the range of time for different crop, different soil, different season? How do we think about that? And sometimes temporal is just seasonal. There's no reason, there's no previous event, it's just seasonal, right? That every dengue season is there in Delhi, so dengue will go up. There's nothing event based about it. Yeah, it's all seasonal. So that's temporal causality. Another notion of causality is what we call structural causality. So the idea there is that you have a complex system like a refinery breaks down. We're going to ask two questions, right? What caused this to fail? And if this failed, what else might fail? So in a structural causality, when things are connected to each other, if something goes wrong in one component, it is both a cause and an effect, right? It is affected by somebody else and it will cause something else to fail, right? So when you go to a doctor and the liver is not functioning, the doctor will ask two questions. Why is the liver not functioning? And if the liver is not functioning, what else might fail? And both directions of causality work in structural causality. So it's a different level at the next level, right? Now, this is a very important slide. This is a skill set that data scientists of the future will need to develop to be able to think about complex systems. And earlier I talked about how complex system is a complex maze of metrics, right? So let's look at that example again, Ola, Uber. So now imagine you have some incentives for drivers. There is an organic demand of cabs and there is some offers to customer. What does that lead to? So that leads to a certain supply of cars and demand of cars in different parts of the city and different times. What does that lead to? That leads to availability of cabs, stock out. If there is very less cabs, then customers are not able to get. Price may change, right? Supply is too high, then prices go down. Supply is too low, prices go up. Utilization is affected, right? If too much supply, cabs are sitting idle and all that. So these are the metrics affected by supply and demand. What does these lead to? These lead to other metrics like fulfillment, conversion, right? How many people got the cab? If pricing was too high, conversion did not happen. People opened the app, looked at the price, did not convert. Or experience is too bad because your cabs are sitting far away and they need 10 minutes, 15 minutes to come. Or the efficiency of the platform is low. Your drivers are waiting more percentage of times than they are in the ride, right? So because of utilization. What does that lead to? That lead to customer metrics like customer engagement, ARPU, right, churn, revenue, cost of running the platform, and all that. What does that lead to? That could lead to market share and profitability. So one of the most important skill sets of the future data scientist is to be able to list out these metrics from across the company, right? Different metrics are owned by people in the company. If we are able to look at all of them and draw this kind of a causality diagram, then I can answer a very simple question that, hey, I want to increase market share. What should I do? So, well, what should you do? You should reduce churn. You should increase engagement. And what should that mean? Therefore, you should increase fulfillment. Therefore, increase conversion. That means pricing should be low. That means supply should be high. Therefore, driver incentive should be high. You see, so this whole idea of connecting the dots forward and backward is an important skill set that future data scientists will have to think about. Yeah. All right. So we understand causality. We understand different types of causality. Now we'll talk about prediction. Prediction is done for four reasons. Across the industry, we only do prediction for four reasons, and I'll talk about that. So let's start with the prediction paradigm itself. Now, one of the most important types of data is what we call longitudinal data. So think of a timeline, think of transactions on the timeline. So these could be your Netflix views by the same account, right? This could be the banking transaction. These could be your medical tests. These could be your grocery shopping, right? So it doesn't matter what kind of transaction it is. Just imagine there is a sequence of transaction tied to the same customer. You have a timeline, right? Now, prediction framework is not interpretation framework. It is a prediction of the future event. So what we do, we think in terms of an observation and say, if I observe what you're doing in the last so many months, days, weeks, we engineer some features and then we predict a future event that is going to happen in the future. So you can think about all kinds of events you can predict. Now, this framework is very universal. It applies to refineries, to telecom, to retail, to insurance, to everywhere, education, agriculture, everywhere, right? Now, the first reason we build prediction models is for intervention. So if you are predicting a negative event like churn of a customer, failure of a part, critical alarm going off, failure of a crop, critical health event in Fitbit. So if you're predicting a negative event, is the first reason we build prediction model, because now we have a time to intervene, right? And say, look, this part is about to fail. There's nothing you can do about it. You better order it early on so you don't have to waste time on shutdown, right? Or if a Fitbit is saying this person is going to get a heart attack in the next 7 years, then how do we intervene now so that it doesn't happen, right? So prediction for intervention, whenever the negative event is being predicted, right? That is called one reason for prediction. The second reason we build prediction models, same framework, is not to intervene but to optimize. So if I'm predicting the stock market or demand forecasting or credit risk of a person or a crop yield of a crop, I'm not doing it to intervene. I'm doing it to prepare myself when it happens, right? So to decide my own actions based on what I'm predicting. Should I sell or buy the stock? Should I stock up more in the inventory or less depending on demand forecasting? Should I give a loan or not? So the bank is not interested in intervening and improving your CIBIL score, is interested in optimizing its own risk reward using the credit models, right? So how do we predict to intervene? How do we predict to optimize? And let me skip that. The next layer is what we call predict for personalization. So if Netflix is predicting that you're going to like this movie or not based on past profile, right? So you can call it a recommendation engine or a campaign personalization, ad personalization, homepage personalization. These are all different types of personalizations where we also predict that he's going to like this YouTube video because he's playing, or in the history he liked these videos, right? So how do we do? Three levels of prediction. for intervention, optimization, and personalization. Fourth level, why do we do interpretation prediction? I'll talk about now, which is in layer 4, right? So now imagine I not only want to predict whether a call drop will happen, but I also want to know why a call drop will happen, right? Because that is more important to me. Because if I can predict a call drop, I cannot intervene. I cannot do real time intervention and say, no, no, don't make a call, your call will drop. Or I cannot optimize my network and point it in your direction, the cell tower, because we don't do it for each person. So we can neither intervene nor optimize. So why do we build a model like this? Call drop model, for example, in telecom. It is neither to intervene nor to optimize. What we do is we do this to explain. So sometimes we build prediction models not because they themselves are useful as is in a real life scenario, but when you do these prediction and say, hey, for the same customer, call A and B dropped, but one of them dropped because of a completely different set of reasons, motion and stationary and coverage was low, and the call B, A was dropped because of a completely different reason. Network load is high and all that. So this is the fourth reason why people build prediction model, only to understand why things are right. So explainability is not just a second class citizen anymore. It is a first class citizen. We are building prediction models not to predict, but to interpret, to explain every prediction. Yeah. So prediction is y of fx, but interpretation explanation is y and e, which means you also produce an explanation along with the outcome and say this is why this call dropped. And by the way, both call drops have the same probability. Yeah. So now the next one we'll talk about is controllability. So the next layer is let me pivot into systems thinking and control system thinking, which is a very important class of thinking which data scientists don't get used to. Yeah? So in these examples, I'm showing you two models, and the colors of the input, there are two colors, right? So the green color things are also causing call drop, and the purple color things are also causing the output, but they play different roles. The green color things are what you can observe but not control, and purple color things are you can control also, right? So in a call drop scenario, you cannot control the network load, you cannot control the outdoor indoor, you cannot ask the person to make a call from outside or stop the car and make a call, or use a different device and not this device, right? So these things you cannot control, but you can observe. That is the difference. And the things like coverage of the cell towers, interference between two cell tower is something you can control. So this ability to divide your causal variables into two subsets, one is observable and one is controllable, is a very important skill set. And that is what leads to the next step, which is what can I do about it, right? So one is prediction of something. Second is what can I do about that prediction. That cannot happen unless we cross the controllability part. So on the output side, we are looking at conversion, for example, on the second example. Now here we are saying that you can only observe the customer preference, that he's a vegetarian, he's married, or whatever. And you can observe what the competitor pricing is. But you cannot control these two things. What you can control is your own discount, your own messaging, your own channel, your own timing, and then the whole thing affects the conversion. So now we have three types of variables, not just input and output. We have controllable input, observable input, and third is the output. So now we need to think differently and not just input output. Yeah. So prediction is y of fx, but now x I'm dividing into two parts, O and C, observable and controllable. Now comes the next thing, right? If you put deep before everything these days, it's more you know sexy or something. So now we'll talk about deep controllability. So we talked about ecosystems which are not run on a single model. So here is an example of three models, right? One is predicting, churn of a customer in telecom. And again, we are going to break down their observable and controllable variables and saying churn can be a function of their behavior, their usage, but their experience, more importantly, which is call drops, call quality, and throughput. All this cause churn. Now, what causes call drop, call quality, and throughput? We go backward and say, if this is my network configuration and all that, observable and controllable, what will it lead to? So, can I pick these experiences in a certain location in a certain time? And now I go back further and say, if I have a network that has a certain cell tower in a certain height, certain azimuth, certain tilt, what would be the coverage and what would be the interference in all the grids? Can I build that model? Think about the cascading effect of the three models. Now, this is a very important skill set again. Today, data scientists are only thinking about building one model well, right? Now we have to think about an ecosystem of models where output of one is an input of the other. Now, the skill set I'm talking about is the connection between a business metric like a churn score with customer experience like call drop, call quality, with operational metrics like coverage and interference, with operational actions like tilt and capacity. So this ability to connect the dots on one side, what can I do on the ground is operational actions. On one side, I have business metrics, and there's a whole layer of causality between here and there and controllability. Now, this ability is what we need to develop next generation systems. How do we think about hundreds of models, and they're organized in a very large graph like this, and now output of this goes into the input of the other, and you can think about controllability, causality in that world. Yeah. Now that you know what you can control, now we are able to do simulations. So now imagine you have built a controllability model. In a way, you have said, okay, I know that conversion depends on these factors. Some of them are observable, some of them are controllable. Let me play with it. So let me play with the discount. Let me play with the messaging. Let me play with this. And if I can change the purples for a given green, I can see the effect of that not by doing the experiment on the ground, but the model tells me that if you do this combination of discount, messaging, channel, timing, what will be the conversion rate on this customer? So now I can play with the joint space of control variables to do simulations for a given input, observable variables, right? Same thing on the other side. Now I can think in terms of saying, okay, given these network load, outdoor, indoor motion, and all that, if I change the coverage here, if I increase, what will happen to call drops in this area? Well, then therefore I should add one more cell tower, right? So the actions are determined by my ability to simulate the actions before taking the actions, because these are very complicated, very expensive actions, right? Putting one cell tower is like 5 crore rupees plus maintenance cost, right? So you have to be very careful about these things. So how do we think about simulation thinking? So controllability is about y function of O and C, but simulation is the ability to say, what if this is the control variable? What if this is the control variable? So now model doesn't have to change. All I'm doing is playing with the control variables only and seeing how the outcome will change. Right? That ability, this is also like a digital twin of that causality. And now you can play with it and see what will happen. Right? This is a very important skill set. And a prediction model should allow me to do simulations. The next thing is deep simulations. Now I can do deep simulations and say, hey, there is a complex network of causality. And what will happen if I change the tilt here? How will it affect coverage and interference in which grids? And depending on the population, how much call drop quality and throughput will it affect for how many people? And therefore, how much churn reduction will happen? So can I build an end-to-end simulation of a complex system? Right? That's a very important skill set. So now imagine you are building a network and you can actually do simulations before you can spend money on putting a tower somewhere. Again, what operational action lead to what metrics, lead to what experience, lead to what business metrics, right? Okay, layer 7 is what we call the optimization layer now. And in this layer, what we are going to do, we are going to think about the real problem in data science. The real problem in data science is not prediction, not just controllability, not just causality, but optimization. So nobody wants you to tell them, "Ki, give me the churn score for tomorrow, whatever." they want to really, the real question they're asking is, what can I do about it, right? How do I minimize churn? How do I maximize engagement? How do I maximize experience? So the real question is an optimization problem. Prediction, causality, controllability are journeys towards solving eventually an optimization problem, right? So in this example, the forward model, given the input, predict the output, is a forward model, but that is not what, that is just a stepping stone. The final answer is not that. The final answer is, what should be my discount messaging channel timing combination that will maximize my conversion rate for a given customer who has these preferences, and in the current scenario where these are the competitor pricing. This is the real question that every marketing guy is asking, right? So prediction played a role, causality played a role, controllability played a role, but the real problem is an inverse problem, right? So you are given that you have to maximize conversion. That means you are given a target output, and you have to optimize the input now, control part of the input, right? So simulation is to do this, but optimization is really the reverse inverse problem, which basically says, give me the optimal control variable C star, where X is given to you and Y you have to maximize. So Y is like saying, I want to maximize conversion rate. Tell me what is the best control parameters. Yeah. And now I can do deep optimization. So I can say, hey, this area has a lot of churn. Why is it so? Oh, therefore I need to decrease call drop, increase call quality. And how should I do it? Go backward and say increase coverage, decrease interference. How should I do it? Change tilt, right? So optimization really gives you the actions you need. Forward pass is only to help in that action, yeah, to help the prediction, but that's not what you want. So it's not enough to say if this is the tilt and capacity, what would be the churn score. The real question is, what is the optimal tilt and capacity so my churn score is minimized? That is the real question. Yeah. So again, going backward from business metrics to operational action, that's a skill set we'll have to develop, both as tools and algorithms as well as the mindset. Yeah. The last layer is what we call the adaptation layer. Now, what happens? The world is constant. Customer preferences have changed. He got married and all that. Competitor has changed. He's changing his strategy. Now he's changing his pricing model. What are you going to do? The causality model is still the same. The black box is still the same. The only thing that has to change is I have to re-optimize, right? For a new set of observed variables, I have to re-optimize my control variables. So that is the adaptation. So the idea is prediction is y of fx, right? Controllability, x is two parts, observed and controllable. Simulation is the ability to try this, try that, and run any number of things with the same forward pass. So simulation is many, many forward passes with random values or whatever values of the input and predict the output. Optimization is the ability to take a particular O vector, the observable vector, target Y, and then say what is the optimal control. And adaptation is the ability to redo this again and again. So as soon as you monitor your customer preference and say that has changed, or you monitor your competitor and say that has changed, it should automatically trigger re-optimization and say now things have changed, the green things have changed, so I need to change my purple things, which are the control variables. Yeah. So how do we think about deep adaptation? So again, let's say the people usage has changed, load has changed, it is different in different parts of the day. Same network, same cell tower has a different load in different parts of the day. And let's say in a particular location, we have added a new cell tower. What are we going to do? Because these complex systems are very dynamic, right? New cell towers are added, morning load is different than evening load and all that. So what are we going to do? We have to keep re-optimizing and saying, tilt and capacity can be changed again and again, because every hour I can change, because my network is different today. Yeah. So that is adaptation. Okay. So hopefully you got a sense that, AI is not just about uh, chat GPT or vision models and all that. there's a lot of layers of thinking that has to go into building a finally a self-adaptive system, right? Imagine a smart city that automatically adapts itself to weather, to new people joining the city, to whatever, right? To holidays. And adaptation is the final holy grail of AI. And if we can build self-adapting smart systems via these different layers, and now you can start to see why each layer is important in the right place to build such a complex system stack. Okay. So thank you so much. I'll take some questions now. And we're all very excited. The people in AI world are very excited about this next 20 years of AI. We are going to do amazing stuff.
Yes, yes, Professor. Thank
Thank
you
you.
so much for that enriching presentation, I must say. A couple of questions that I can see here. Maybe I'll start with a few ones. Okay, there's one which says that while we've very clearly called out the architecture of AI, when should we bring aspects about the cost of building this particular system into picture?
Yes, very good question. So there are two types of cost, right? So one is sort of, let's say there is a pre-trained model that you're using, right? So you're buying commodity models from the, now that cost is coming down because a lot of models are being open source, right? So that cost
Yeah,
is coming down,
right.
but still that is the cost, right? So how do we think about an API cost per model? Should I build my own? Should I buy a model? Will it work on my data, my thing? All these decisions have to go. And then clearly there is a hardware cost, the network cost, and hosting these models and running thousands of API calls. We all know ChatGPT spends $700,000 per day,
Correct.
right? So
Right.
it's a cost, not free, right? We but then we have to do a cost benefit analysis and say, is the cost worth the benefit, right? If I'm saving 1 crore rupees per day versus spending 50 lakhs per day, then I'm doing a, so that is one.
There.
Second is in the long term, all these costs are going to come down. The cloud cost is coming down, the model cost is coming down as more and more people, and because of open source movement, a lot of things are now free. So I think in the future, the gap between the cost and the benefit will increase only, and benefit will be a lot more than the cost. But we have to do it smartly. Otherwise, we'll waste our money on the wrong model too early, and then we say
Right.
AI doesn't work, right? So we have to be smart.
Right.
It's a
So does it make sense to say that maybe we pick the low-hanging fruits, models which are easily available or more readily available in the market, either free or at low cost, and then pick them up and then build a strategy around them?
the way I do it is I look at every API and say what is the impact of this versus what is the effort in this. So if you think about the impact versus effort,
Effort.
and now
Okay.
you say I want to pick the high impact, low effort. Effort would be cost, right? People effort.
Right, 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 right.
So high impact, low cost is how you start, and then you prioritize based on that. So there has to be systematic prioritization. There also has to be a honest evaluation of your ROI, not just thinking about it or making it up, but say, let me try this at only 0.1% of the data and see if it is worth it, right? And that's how people do cost benefit analysis and then scale. Yeah,
Okay.
but that's a
So,
good
yeah,
question.
Professor, we have another question regarding the performance of the deployed models.
Mhm.
How do we monitor the ongoing performance of the models? Or, I mean, just to extend it probably a little further, how do we make sure that they are getting updated as per the business needs?
Yeah. Sorry, I was reading another question. You're
Okay.
talking about the monitoring of the model. Right? See, there is a
Right,
whole,
right.
so think in terms of a model life cycle. So there's a life cycle. We think about customer life cycle in a business. Similarly, we need to think about a model life cycle, right? So the idea is a model is born because it was designed by some data scientist, it was trained on a certain data, then deployed, then it gets, before it gets deployed, you do benchmarking on it, you do A/B testing on it, then you deploy it, and
Okay.
then you start monitoring it and see the drift, right? And saying, look, over a period of time, features have changed. So there is a feature drift, there is a distribution change, there is a prior of the class has changed. so the model is not valid anymore. And you have to continuously benchmark the model. Model is not a static thing. It has to continuously update. Human brain changes every single day, right? We do a delta training every single day. So our models are current, right? So we need a framework like that, which is a continuously, like you talk about CI/CD pipeline in software, right? We need to add a CM, which is called a continuous modeling also, which is not continuous, but let's say daily, weekly, monthly, so that our models are quote unquote current, because they do drift, because the data drifts. Summer models are not same as winter models and all that. So we need to
Right.
keep an eye on that. Depending on the domain, we can figure that out, right? And,
Right.
yeah, that's a very important part of the model management life cycle.
Model management. Right. Right. Professor, during today's day, the topic being AI and corporate innovation, we had a very interesting conversation with three lawyers across the globe. So we had a panel from Brazil, we had a panel participation from India as well as from UK, and the conversation was around the impact of Chat GPT. We coined it the new paralegal, in the world. So, any thoughts on that?
Yeah, so I think it's a great productivity tool is the first use case, right? Whatever we were doing
Right,
on
right.
Google search, now we can do it. So if you think about a software engineer doing a Google search on OpenStack to find a piece of code, can now actually copy paste it from ChatGPT by explaining what they want to do. So the interface is still the same, right? You put a query or a
Correct. Right,
prompt,
right,
you get
right.
in one case you get 10 blue links and you have to figure out your answer. In one case you directly get the answer because what I call the librarian has read all the books now, right? So think about the
Okay,
paradigm
okay.
shift, which is earlier you
Right.
go to a librarian and
Interesting.
say, I want this. He will point you to a book and say, go find your answer there. But now the librarian has read all the books. So now you go to the same librarian, he can tell you the answer, right? And he doesn't know that he got the answer because he's read 1,000 books and he's a combination.
Right.
Now, uh, so there are multiple things to worry about. There are still limitations to ChatGPT. I'll just talk about few.
Right.
So one is we need to be careful about moving our data into the prompt.
Right.
So it
Right.
doesn't go outside. Because once you do that, you have no control over it because OpenAI and others they will use it as training data, and you have signed that agreement already. So we need to be very careful what we prompt engineer. Second is ChatGPT is going to give me a generic answer. What about personalized answer? Right. So the idea is, let's say if I ask ChatGPT, hey, tell me what movies should I watch? It will not tell me an answer based on what I liked because those
Correct.
that data is my personal data. So the next evolution of ChatGPT is another system which takes the prompt on one side, takes the personal data on one side, and then uses ChatGPT capability to generate the answer which is personalized for you, not a generic answer that a librarian will give you by reading all the generic books. Right. So that is the
Right.
second part. Third part is now ChatGPT will move into actions and not just information.
Okay.
So the idea is, Google search was an information system. You can find where the movies are playing, what the reviews are, but you could not buy a movie ticket on Google. You had to go to a book my show. So there is a difference between information and action. And that's why
Actions. Right.
Yatra.com, all these are action companies. Google is an
Correct.
information system. Now, ChatGPT should not make the same mistake and say, I'm just going to stay an information system and give you
Okay.
a prompt answer, but I should be able to convert not just answers but actions and say, so if I ask ChatGPT, book a show for me, it should be able to convert that to an action. It doesn't have to tell me a very nicely written English text because that's not what. So information needs is different, action need is different. So ChatGPT becoming personalized, ChatGPT taking actions are the two big next steps. Third is obviously reasoning and all that. A lot of people are struggling between the idea whether it thinks like a human or it only regurgitates the next word given the last 10 words without
Right.
understanding anything. Right? So there's a debate going on. Jan LeCun on one side and Hinton on one side and all that. But
Right.
a lot of theoretical frameworks will emerge where we'll really understand what is going on inside. So what is coming out is very fascinating, but for it, it's just a sequence of symbol. It's not a real life experience, right? So there's a big difference in how humans do the same thing. When you ask a child to write an essay on something, that is not doing it because he's read billions of essays and now he's just regurgitating words after word. The child is writing because of his life
Correct.
experience. There's a huge difference between what ChatGPT does and what really AI is. Let's not get carried away. It's a very fantastic thing, but it's not the end of the world. But we have to use it in the right way, and I think what will happen, the role of the humans will go from being a creator to a curator now. So
Right.
if you think about a journalist trying to write a news article, they will give a prompt. The article will come from ChatGPT. They'll only curate it, just fix a few things here and there and publish. Right? Make to fact check and all that. Similarly, if I have to write a report for a X-ray, and there is a vision that the radiologist will not have to write the whole thing, but curate what AI is generating. So the role of the human expert is moving from creator to curator. This paradigm shift we have to accept and celebrate, and not worry that our jobs are lost. We are still having a
Right.
job, but we are becoming 10x more efficient.
More efficient. Right. I think on that super positive note, we close the session today, Professor. Thank you so much. It's always been a pleasure having you.
Thank you. My pleasure. Yeah. Please connect online and if you have more questions. Thank you.
Sure, definitely, Professor.